Hello students, and welcome to our final lecture video. So we made it through the semester. So we covered a lot this semester, right? We're finally on our last lab where we're going to be talking about one of my favorite experiments, the double slit experiment. And this is where we're going to learn that light can behave as a particle as well as a wave. And in fact, electrons can do the same thing too. Sometimes electrons could behave as a particle and a wave. So this is kind of how all this stuff starts to tie together. So really we learned a lot this semester, right? So we learned about very early fundamental things about electrons and protons, right? Or how charges behave. And we learned that these charges, they can have forces on each other. And because of those forces, we can, start engineering devices like capacitors, resistors, and we could utilize this in such a way to start, powering our devices using simple circuits, and then we could use like Kirchhoff's rules to help us model those circuits a little bit better, right? So then we went into light. How does light behave? And we went into very simple properties in optical systems with thin lenses and concave mirrors. And now we're going to talk about some of the more advanced behaviors of light. We're going to be doing the Thomas Young's experiments, which shows that light behaves as a wave, but light could also behave as a particle. And this is very fascinating, right? So photons and electrons, they actually both have this phenomenon. In fact, Albert Einstein called this spooky, right? How can light behave as a particle and a wave? But one of the things I want to point out this semester, what you should have learned, is basically all this physics and physics 2 makes up our whole world, our whole reality, right? Everything that you have, every object that you have has protons and electrons, so there's electrical forces present, right? Everything that we see has photons, right? Our feel, our internet, and everything. So this fundamental physics makes up our whole entire reality, which I find fascinating. And there's a lot of questions that are still unanswered, and this is where it comes from. Some of the modern physics, right? And this it comes from this double slit experiment. So why is a double slit experiment fascinating, right? Well, it's fascinating because, we don't really quite understand, and it starts getting into quantum mechanics, and it's a little bit more advanced for this course, but I just want to give you a little peek into what we do. So I'm going to attach a video. It's a little cartoon, and it's introductory to this idea, and it does a really great job at explaining the double slit experiment, even better than I can, and it's entertaining. I show it to my students every year when I teach in person, and everybody always enjoys the video. It's very short. I highly recommend watching it because you should be at least a little bit entertained. But essentially, you have, when you look where light is going, or you measure, if it acts like a particle, you'll get two little lines, right? And then if you shine light and it acts like a wave, you'll get this nice little diffraction pattern. Now, there's multiple experiments that show both cases. We're going to be doing the Thomas Young experiment, which demonstrates how light acts like a wave, and we're going to be investigating those wave-like properties and coming up with equations that explains this system, which I'll show you on the next slide. Now, the video that I'll attach will explain this and leave you with the questions that almost all physicists have. Why does it behave that way? We don't know. But it's an interesting video, so please watch that video and you'll have your mind blown. But like I said, we're going to be doing the Thomas Young experiment. So Thomas Young demonstrated that light can behave like a wave, right? So when you shine it through those double slits, you'll get a diffraction pattern that looks something like this, right? In this image. So basically what we want to do is we want to show that depending, where our apertures are, these little holes given by a distance d, when we shine this light through, we're going to get these little bright spots and dark spots. Now, the video that I will show you will explain the bright spots and dark spots, but essentially the bright spots are where the waves add together, and the dark spots are where the waves cancel out, right? So the video that I'll attach will talk about the behaviors of light, so you could understand why you have these bright spots and dark spots. But our goal is to basically use some simple geometry to say, hey, where are these bright spots at, right? So this little C right here is called your central maximum. So this is your main bright spot. And we always count these using this integer n. So at C, it's 0. Below C, it's -1. Above C is 1. You kind of get the point. So this would be 1, 2, 3. Below it would be -1, -2, -3. So you should get the point there. So yes, so we're also going to say that there's going to be a distance between these apertures or these two little holes of L, and then what we're going to want to do is find the location of this Y. So using some geometry and some things that we know, we could come up with this equation, right? Where d sine of theta will equal to n lambda. So this lambda right here, it's your wavelength. Remember, n is depending on where these are at, right? But lambda is your wavelength. So depending on what wavelength of light you have, it'll change. So if you remember in my introductory video, we talked about wavelength of light, and I said for the most part we're going to be talking about white light. Well, now we're going to get wavelength specific, so we could say, hey, we have a wavelength of 400 nanometers, purplish light, or 500 nanometers, which is like yellowish light, or so forth. So pay attention to, in your simulations, to what wavelengths you're using, because that will change. But yes, we have this equation. Now, if you're not, we are algebra based, but if you're not up on your math, sometimes we do apply this idea. It's called a small angle approximation. It's basically when you have small angles, so we just do an approximation. So when we do that approximation, we could rewrite this equation using d tangent theta, all right? And the reason why we want to do this is because we know something about tangent, right? And we know that tangent theta is equal to the opposite over adjacent, right? And in our case, we want to know, right, the height. So the opposite of the triangle would be this y right here. And then the adjacent would be this L. So now we have y over L. So then we're just going to substitute that back into this equation. So now we have d is equal to y of n over L, where n is depending on where it's at. So if you have y of n1, then we have the distance between your central maximum up to there. So that makes sense, right? So that's just giving that. So now we could solve for y because we want to know the location of these bright spots, and we have y of n is equal to this. So this is basically the main equations and how we get there. Again, all these equations are doing is we're trying to describe where are these bright spots in the waves. N is basically the number of spots that you have, right? And distance between, your apertures are these little holes in the screen. And then D is going to be the difference of these holes in the middle, right? So we go right here to right there. So D is the distance, and it's pretty straightforward. And L and lambda is your wavelength. Again, another thing that could be useful to know, I'm not going to go through it, but another thing that could be useful to know is what the angles these are, right? So like, for example, you might not want to know what position it is in the y direction. You might want to use theta. So you might want to say, okay, at theta 15 degrees, we're going to have this bright spot here. So this is the equation that expresses the angle of this. So it'll tell you what angle this is at for a bright spot. So let's say there's a bright spot here. It'll give you the angle of that. So this is the equation that expresses that. It's basically telling you the same thing, just using a different coordinate system, right? So this tells you the y position. This tells you the theta it has to be to get to that y position. But so those are your two equations that could express the location of these bright spots. So that's basically what we're doing. It's our last lab, so you made it this far. So we'll just get through one more. So I'll post this video, and then I'll attach the other video. And as always, if you have any questions, feel free to reach out. Thank you.